Hello, my name is Dan Wiener, and I will be reviewing a 2012 paper from the IEEE Symposium on 3D User Interfaces. The paper is called Comparison of a Two-Handed Interface to a Wand Interface and a Mouse Interface for Fundamental 3D Tasks. Quite a mouthful. It's by these people here, and it's a direct empirical comparison of three ways to control 3D objects. And one of its authors, Jason Gerald, actually wrote our course textbook, the VR book. In this presentation, I'll cover the problem this paper tackles, and how the study was designed and what they found. So, the core problem when manipulating a 3D object is dimensionality. To manipulate an object means to move it, rotate it, scale it, and this means controlling 6 degrees of freedom. 3 degrees are used to represent the position on the x-axis, the y-axis, and the z-axis, and there are also 3 degrees to represent the rotation of the object, yaw, pitch, and roll. We use mice all the time in our work with computers, so they're very familiar, but computers usually only need us to work in 2 dimensions. And that's perfect for a mouse because that's all it can sense. But when we need to do 3D work with a mouse, you need to constantly switch modes. So first you're in translate mode, then rotate mode, then change axis mode. That interaction is slow, and it breaks the feeling of directly handling an object. So the authors asked whether the input devices that physically match the 3D nature of the task can close that gap. They mention a lot of previous studies that had holes on this subject, and they were attempting to conduct an extremely empirical study of the input tool's effect on 3D task times while trying to remove all other variables. The image below shows the 3 types of operations you can perform on a 3D object. So this one is translation, this is scaling in the middle, and on the far right is rotation. So the study pits 3 interfaces against each other. The mouse is the familiar 2D baseline. There is a wand, which is a single track device held in one hand, giving direct 3D control. And the two-handed interface, which is the paper's actual contribution, gives each hand its own track device. So you can grab, orient, and reposition with both hands at once. The progression is essentially 2 degrees of freedom to 6 degrees of freedom with one hand to a full bimanual spatial interface. The question is, which of these lets people complete fundamental 3D tasks fastest, and which they actually prefer? So below, you can see the table from the paper explaining the interfaces and their capabilities. The degrees of freedom are the interfaces tracking in 2 dimensions or full 3 dimensions, which is the mouse is 2, meaning the x and the y axis. The wand is 6 because it's one-handed x, y, z axis, yaw, pitch, and roll rotation. And the two-handed interface, or THI, has the same thing as the wand, but in both hands. That's why it's 6 plus 6. The viewpoint translation is being able to move an object around the screen. This is seen in the figure on the right. This is the left image, which we saw in the previous slide. Viewpoint scale is being able to scale an object in size by basically grabbing and stretching or pinching it together. This is the image in the middle. And viewpoint rotation is being able to rotate an object and by grabbing it with both hands again. And this is the image on the right. The paper didn't really go into this, but with some further research, I found that integral is the ability of a device to control multiple dimensions of a 3D object at once, such as translation and rotation at the same time. All of these interactions actually happened around a central point between the user's hands when using the two-handed interface. There will be more on that later, but special modifications had to be made to the system to make tasks more accessible to the users with more than just the two-handed interface, for the mouse as well. And finally, the authors also tested stereoscopic versus monoscopic view to see if this made a difference in 3D task completion. Now, stereoscopic view is when you have two, it's basically how our eyes work. You have two images of the environment that are slightly offset to give you a more 3D view of the world. Monoscopic view is where you only have one image of the environment, which gives you a more flat. If you hold your one of your eyes closed, you lose your depth perception essentially. So they wanted to test that as well to see if to basically isolate what actually helps these fundamental 3D task completions. So the two-handed interface is the paper's real contribution. The idea is to mirror how we handle real objects. One hand can hold and orient something, while the other hand adjusts the view or grabs a second point, both hands contributing simultaneously rather than taking turns. This bimanual approach later became the foundation of commercial systems like MakeVR and iMedic medical environment. It's worth noting that this was purpose-built special hardware, not a consumer controller like we have now with the Quest 3 and the Vive and all of that. So on the images below, on the left you can see an image of the 3D object with all its axes available for selection. This involves translation and rotation. This was the way users had to interact with objects when using a mouse, and this was special made for the system to allow mouse users to basically have a competitive edge, because they would have no chance if they didn't have at least this affordance. And on the right you can see the two controllers. This is the two-handed interface on the right. The two controllers are the balls with the spindle between them marking the center point, because the center point was the point of manipulation for the user, and this was one of the accessibility affordances that they implemented, since users found it difficult to know where that axis of manipulation was, because it was dependent on hand placement. Without the spindle, it was kind of hard to tell, and they were using before they had this, they were basically using the occlusion of the objects, trying to stick their hand through the object to see where they were in the scene. And once they added the spindle, it became much easier for users. So they did two tasks with 20 participants. The first task was a docking task, which had moving and orienting an object until it matched a target pose, and this was a measure of basic 6 degrees of freedom manipulation. The second was a construction task, assembling objects into a structure that you see on the upper left of the right side of the image, which is more realistic and involves moving the viewpoint. That was intended, at least. They tested each interface on both a monoscopic and stereoscopic display, so they could separate the effect of the input device from the 3D depth on the screen. The headline result was speed. Trained participants completed the task roughly 4.5 to 4.7 times faster with the two-handed interface than with the mouse. Against the one-handed wand, the gain was smaller but still real, between 1.3 and 2.5 times faster. So adding the second hand wasn't just a marginal improvement. Matching the input to the dimensionality of the task produced a large, consistent performance jump. Users did manage to game the construction task a bit. Instead of rotating the viewpoint as intended, they utilized the object collision to force the blocks into place. The results still stand, however. And here we can see that training times were what made the difference. The time invested in learning the two-handed interface did pay off for users, but it takes longer to master. The authors also found that users were more capable of playing the Wii, which also used the Nintendo Wii before the actual construction tasks, which also utilizes a wand-like controller. They turned out to be much faster and better at using the two-handed interface. So preference tracked performance closely. 19 of the 20 participants preferred the two-handed interface over both the mouse and the wand, and comfort was high. 16 reported feeling very comfortable with it, and the remaining 4 just comfortable, with no one reporting discomfort. That alignment between objective speed and subjective preference strengthens the case. People weren't just faster, they liked it more as well. As for the display, it did not matter. No statistically significant difference was found between mono and stereo, but 17 of 20 users did say that they preferred the stereo display. This shows us that the input device really drove performance, not screen depth. And an expert study was also performed to confirm the results with genuine expert users of the three interfaces, and the results were even more dramatic. Average docking times of two-handed interface users were 4.5 seconds, while wand users were 14.5 seconds, and mouse users almost 40 seconds. This shows that experience pays off even more as you gain it, since THI, two-handed interface, I abbreviated it, two-handed interface users yielded task times 3.2 times as fast as the wand and nearly 8.8 times as fast as the mouse. So why does the bimanual interface win? Three reasons really stand out. First is the dimensionality. The device offers the same 6 degrees of freedom the task demands, eliminating mode switching. Second, proprioception. You know where your hands are without looking, so spatial control feels direct. And third, real-world mapping. Using two hands to position and frame an object is how we manipulate physical things, so there's almost nothing to learn. The performance gain is the payoff of removing the translation layer between intent and action. A few limitations are worth noting. The participants had to be trained, so these numbers reflect skilled use, not first-time performance. The two-handed setup was specialized research hardware, which, it's not commercial hardware. The tasks, docking, and construction are fundamental but very narrow. It doesn't cover every type of 3D kind of work. And with 20 participants, that is a very modest sample. None of this undermines the finding, but it does bound how far we should generalize it. And the conclusion: the closer your input maps to the 3D structure of the test, the better people perform. To wrap this up, the study showed that the two-handed spatial interface dramatically outperformed a wand and a mouse on fundamental 3D tasks. Thank you so much.